hearing me clearly. Okay, thanks for confirming that. I want to welcome you to my lecture today. And of course, today the focus is actually going to be on deep learning. In today's outline, I'm actually going to walk everyone through what I call, why deep learning and why now. Then I'm also going to discuss the concept of perceptron as it is used in deep learning. Then from there, the focus is going to be on building neural network with perceptron. Then finally, I'm actually going to walk us through how to apply neural network. Okay, so what is deep learning? I'm actually going to say deep learning is a subset of machine learning, and machine learning is a subset of artificial intelligence. The artificial intelligence technology is changing the way we interact and the way we analyze the world on a daily basis. Why do we need to analyze the world on a daily basis? Because we find ourselves in a world where we basically want to have an understanding of what is going on so that we'll be able to take a correct decision. We don't want to take a decision that we're basically going to regret. And that is the reason why we actually moving in the direction of, using artificial intelligence. So I'm going to say both machine learning and deep learning are powerful artificial intelligence tools. But I'm going to say distinction exists between machine learning and deep learning. Okay, so, and of course, in artificial intelligence in general, we actually talking about technique that will enable our computer to mimic human behavior. Of course, we actually want a situation whereby things can be simplified. Can we have a way that the computer can just behave the way human being behaves? And of course, I walk you through machine learning the other time is when we're using the computer, the database management to learn insights from data. So with the deep learning now, what we basically mean by the deep learning is more or less like a way of extracting pattern from data using neural network. Okay, so which means the deep learning is a form of a neural network model. Okay, so I'm actually gonna walk us through all this, but the fact remain that just as machine learning is a subset of artificial intelligence, okay, the deep learning is a subset of machine learning. Okay, only that the takeaway from here is that with a deep learning structure, we can actually use artificial neural network that consists of many different algorithms. You remember the other time when I was walking you through machine learning, I said, what we intend to achieve with the machine learning, can we have a way the algorithm can actually be used to learn model, okay, from data. Okay, I believe you actually remember that. Okay, so the deep learning system is capable of operating without direct labeling from its curators. And I'm going to say they have the potential to perform more in-depth roles. That's why we call it deep. We're actually going more deep, okay? So it's like going more deep into the data set, using some architecture. Okay, so and I'm gonna say so the next is why now. Okay, some of you are aware that neural network has been here for a long time. Okay, so why the resurgence? You know, the resurgence is just that things are changing in the world. I'm gonna say uh in five, let me just say um more than 95% of data set in the world today, you know, are actually you know we actually obtained that in less than five, let me get 5 years ago. Okay, I'm going to say this again. More data every day by day with the evolution of Facebook, Instagram, TikTok, Twitter, and so on like that. You know, there's a large evolution of data. And let me tell you this, the conventional method approach that we use may actually struggle with that. And that is the reason why we basically want to go in the way of technology. Okay, so that's we're going to go in the way of technology. You know, we actually going to actually how can we actually program, how can we actually investigate, and how can we actually analyze pattern in data. Okay, this time around we're not talking about small data set, we're talking about a big evolution of data. Okay, we're talking about large data set. Okay, so that's number one. So which we call big data. So neural network, the deep network, the machine learning, of course, they actually have, success story with big data. Now, the second reason why we're going to be focusing on deep learning now is the hardware. Okay, looking at the hardware, in the world now, we got a lot of, going, if you look at the advancement in technology, there have been new, discoveries of this. And of course, with this, the technique of, the neural network, can actually be used, okay, because we had hardware that we hate that. Then what about software? You know, we have improved techniques, improved models, toolboxes, and so on like that. And that is the reason why we actually need our deep network now. Okay, so when we talk about deep learning, uh, I'm actually going to show you the network architecture now. That we call the perceptron. Okay, the perceptron is also called. We want to talk about the forward propagation, where we basically gonna start from input data. The input data, you have x1, x2 up to xm. You have m numbers of features that we call in statistics independent variables, or you call them explanatory variables, or you call them predictors. And of course, using perceptron now, we basically going to assign weight to each of the feature. Okay, when you take a look at feature X1 now, I actually have a weight W1, and feature S2 has a W2 as weight, and so on up to feature XN. We got weight. Okay, the weight is going to tell us the strength of the node. These are each, this is a node right now. Okay, the strength of the node is actually what the weight is actually representing. Now, there's going to be a kind of linear combination where we're going to multiply weight by x1, multiply w2 by x2, up to multiplying, you know, wm by xn, and we're going to sum them. Okay, which is exactly what we have here, right? Okay, so that is the sum. And on getting to this junction, we basically going to have an activation function. The activation function, we actually induce nonlinearity into the show. Okay, we got different kind of activation function that I'm actually going to talk about as time goes on. The activation function, we got different kinds of them. Okay, we got different kinds of them. Okay, so and at the end of the day, we basically going to have an output. The output may be maybe we're working on a classification problem, or we may want to make a prediction, but today I'm actually going to focus on a classification problem, where the output y curve is basically going to be categorical. Okay, so as you can see, this is the architecture or using the network. We're actually going to go from input to weight to sum, and to the activation function that we induce non-linearity, and finally to the output. Okay, so I want to spend more time on that again. When you take a look at this guy here, this is representing that in a scalar form. What else if I actually want to do that in a matrix form, where I'm actually gonna say X here, design matrix X is gonna be n by one, which means we have m numbers of features, and we basically going to have weight as well. That's also going to be n by one. Since we basically going to assign a particular weight to a particular features, the numbers of weight we basically going to have is going to be the same as the number of weights. Okay, so um, let me just say that when you take a look at this junction now, give me 1 second. I want to check on something. Okay, I think everything is good. So sorry about that. Okay, so as I was saying, there's going to be a linear combination between weights and the features. Some of you may be wondering, what is this guy doing here? Of course, where the W0 weight is more or less like an intercept in a linear model. And of course, the coefficient of the intercept is 1. I think you know that, right? Okay, so that is the reason why we have that. So those of you that are familiar with the linear regression, you basically, if you have y equal to x beta, okay, for those of you that are familiar with the linear regression model, okay, my design matrix X is basically, we're going to have like 1, 1, 1, until you get to the last one. And basically, maybe we have like 2, 4, 7, whatever, until you get to 10. For situation where we have simple linear regression model with one predictor, of course, this is going to be like X, okay? And Y, we can actually call this guy X0. Maybe we call this guy X1. So this is just a constant, okay? So which means if I want to write that in a scalar form, I'm basically going to have beta naught, okay, plus beta 1 X1. I think you get that right. Okay, so if that is taken now, if you really understand that now, so you know that there's going to be, for every feature, there actually going to be a weight attached to that. And of course, there's going to be a linear combination between the weight and the corresponding, and their corresponding inputs. Okay, and at the end of the day, we're actually going to add them up. Okay, when you add them up, the activation function will induce non-linearity. Okay, activation function will induce nonlinearity, and at the end of the day, we're basically going to have our output. But let me tell you this, a lot of stuff is going to be going on here, okay, which we call the activation function. Okay, the activation function is going to make the curve to go up and down. Okay, so the activation function can actually be a sigmoid. It can be a sigmoid function that is going to look like this. When you take a look at this guy now, so you're basically going to see the range of response here is going from 0 to 1. Don't forget, we basically well, the nature of the response variable, the output variable is categorical, right? So which is more or less going to be binary, like 0 to 1 stuff, right? Okay, just wanted to take note of that. Okay, now apart from the sigmoid function, we can also have other activation function that can be used, because for different scenario, for different kind of situation, we basically a particular activation function may be appropriate. Okay, so what I'm trying to show you now, don't forget I said the activation function is the one that can actually induce non-linearity, okay, into the architecture. And of course, there are different kinds of them. So we have this a sigmoid function, this hyperbolic tangent, and this is what we call the rectified linear unit. And of course, this is a function, the sigmoid, okay, this is hyperbolic, okay, and this is a rectified linear unit. And of course, this is a derivative of this guy here, this is a derivative of that. You know, you may be wondering, why do we actually need the derivative? Of course, we actually going to need that because we may want to measure the rate of change, okay, so which is actually very important in deep learning. Of course, basically going to be using Python program for this, you know, Python software. If you actually want to have access to, you know, Sigma function using Python, this is the code. And of course, if you want to have access to hyperbolic target, this is the code using Python. And if you want to have access to the rectify linear unit, this is the code in Python. And I also want to let everybody knows that you know, the three activation functions introduced here are non-linear. And don't forget that I said the activation function induce non-linearity into the deep network architecture. Okay, so what is the importance of the activation function? Okay, like I said, the purpose of activation function is to introduce non-linearity into the network. Let me tell you this, before we can actually apply neural network model, of course, we actually, we realize that this situation is highly complicated. Okay, highly complicated. And that's why when a real life situation is highly complicated, of course, the form of activation function that is actually going to work is the one that can induce non-linearity, okay, into the network. Okay, so let's say the problem at hand, we actually want to build a network that can make a distinction between green and red points. As you can see, the green and red point actually scattered away. Okay, you know, some of you may be wondering why we actually need an activation function that's going to induce non-linearity. As you can see right here, if you make an attempt to use a straight line, of course, it's going to look this way. Take a look at that. So, which means you basically going to have green and red in a particular region, and that's not appropriate, or which means you know, the classification has not been done the way it should be, because if you really want to classify, you know, two, we want to classify item into two distinct group. So which means we should, in one particular spot, we basically need to have, you know, item of the same color. That is the way it should be. Okay, so and also I said the linear activation function produce linear decision no matter the network size. But let me tell you the appropriate one that we have to take a look at it. This is non-linearity now. So as you can see, this actually group, you can see the green is in a one class and the red one is in a different class. So this is a complexity that we're talking about. So non-linearity allow us to approximate arbitrarily complex functions, okay, compared to linear. Okay, so going to perceptron now. Okay, going to perceptron now. Okay, perceptron is actually a single layer neural network. Okay, and a multi-layer perceptron is called neural networks. I just wanted to say that one is a singular, the other one is a plural. Okay, when you talk about perceptron, you're actually referring to a single layer in neural network. In neural network, we got layers. The layers actually contain the neurons. There's something that we call the ED neurons, okay, which more or less look like that of the human brain. Of course, we're trying to mimic human brain. Okay, so the multi-layer perception is actually called neural networks. But you know what, the perceptron I'm actually talking about is going to be a linear classifier. We're going to be working on a supervised learning right here, where we already, for every input, you have an output label, and you basically want to use your knowledge of the input to make a classification. You remember the example that I cited in the in my earlier video, where we are actually want to classify, where we want to classify you know item, like some people apply for credit card, and you actually want to see whether they should be granted or not, using their credit history, using the gender, whether they own their house or they got job. Okay, so we got features, and you also have an output label, which is we call that a supervised learning. So we can use a deep learning to make that kind of classification as well. You remember in my previous lecture, we talked about how decision trees, the KNN, can also be used to do a classification problem. Okay, so the perceptron was used to classify data, okay, into two parts. Okay, the example is what I actually gave the other time about some applicants, those who apply for credit card, and whether they're going to get approved or not. Okay, so take a look at what I have here now. The perceptron will enable you to use it, to classify, the blue point from the red point. Take a look at what we see here. Okay, so it's just like you basically have some features, and the output on each on these features is either is going to be a cat or a dog. And what we basically want to say, want to do is, if I based on the observations of some features, can I actually identify a new animal that we haven't seen, but we only see its features? Can we actually identify that to be cat if it's a cat? If you're able to do that, of course, it means we got it right. And if it is a cat and we use a model, to figure that out, and that turned out to be an animal other than cat, then we got it wrong. Okay, we got it wrong. Okay, so I'm actually going to walk you through the perceptron right now. Okay, this is the basic architecture. We basically going to have a set of inputs that we call features, and for every input, you're basically going to have weight. And of course, the sum here is just going to talk about linear combination of the weight and features. And of course, this is where the activation function that you are using is is going to act. And of course, finally, you're actually going to have an output. Okay, so which means in the perceptron, we got 4 components, the input values that I show right here, the weight, okay, the sum, okay, the activation function, then the weight, the weight and bias, some of you may actually, be wondering what is the essence of the weight, the weight is actually is going to tell us the strength, okay, the strength of the node, okay, it's going to tell us the strength of each node. Okay, these are the node, like the strength of x1 now is W1, the strength of x2 is W2, the strength of xn minus 1 is going to be Wn minus 1, and of course the strength of xn is basically going to be Wn, okay, and we actually believe that when you're applying a neural network model, okay, the output is basically going to be the sum. Don't forget I said the sum, and we're actually going to have a linear combination of weights and the input, right? And of course, we're basically going to sum them. So let me just write something like this. The linear combination of weight and input. And not only that, we're also going to have bias. Okay, we're going to have bias. The difference between this and what we have in a linear regression model when you are using statistical framework, okay, we normally have the deterministic part of the model. For instance, let me write the replica from the statistical framework. Okay, if I have this in matrix form, I'm actually going to have what we call error, right? You remember that? Where this side is the systematic part of the model, which we call the deterministic part of the model. And of course, the other part is the error, which we call the unexplained variation. And this guy is the explained variation. Of course, the variation around the response is total variation. But let me tell you the way the network actually work. We believe that the output in the network can actually be written as a linear combination of the weight and the input plus the bias. Okay, so that is what I actually wanted to take note. And the bias are actually like a constant, okay, which they are an additional input, okay, into the next layer that we always have the values of 1. Okay, so bias units are not influenced by the previous layer. I just wanted to know that. I'm going to say that again. Bias units are not influenced by the previous layer. Okay, but they do have a growing connection with their own weights. Okay, and another thing, another important role of the bias is that it guarantees that even when all the inputs are 0, okay, then there will still be an activation in the neuron. Okay, so I wanted to take notes of that. Okay, I'm going to clean up now. Okay, so the way the perceptron work, of course, I said, no, you actually, the step number 1, you have some set of features, right? And each feature actually have The feature, let's say the set of inputs, and each of them has their corresponding weight. And of course, here is where you're going to have a sum, like here, this multiplied by this, that multiplied by that, this multiplied by that, and so on like that, depending on the number of input, excuse me, that you have. Then you're going to sum them together. So right here, you are more or less having like summation xi, okay, wi, okay, where I actually start from 1, like in this scenario now, to 5. Okay, so take a look at that. Okay, and maybe you want to do a classification problem where it's either this or that. I'm talking about binary, so we're going to use a label 0 or 1. Okay. Okay, so the next thing is, I think I just explained this guy now, that you're basically going to have weighted sum, right? Okay, now in the activation function, okay, when you apply that weighted sum, okay, to the correct activation function, okay, the activation function is, the f of s can be equal to 0 or 1. Don't forget, we're talking about, something that has to do with categorical, well, what is the condition for f of s to be equal to 0 is that x has to be less than 0. Probably s has to be, and that was why I said with 0 greater than s. So if you want to rewrite that, it means s less than 0, which means negative x, and f of s equal to 1, you're talking about non-negative, okay, 0, and so on like that. And that is why you actually have for 0, and that's why you have this guy. When you take a look at we got to side of x, okay, at 0 here, okay, at 0, okay, when y equal to 0, you are actually referring to the negative side of x, right? And when s is non-negative, okay, probably right here, you actually, f of s is going to be equal to 1. So that is a threshold. Okay, so I'm going to give a structural example now. We got input, we got 4 input, which are PZ 1 to 4. And of course, each of them has an input layer, X1, X2, X3, X4. And of course, maybe because there are 4 of them, and we realize that they are equally weighted, and the weight for each of them is going to be 1 over 4, 1 over 4, 1 over 4, that we call 0.25. And of course, we basically going to have the combination of these and that. You get that now, which is what we have here. And there's going to be an activation function such that, when s is greater than negative 0.1, it's basically going to be that. Otherwise, it's going to be that. And of course, the label category could be bright or dark. Maybe we actually want to classify different kind of pieces that we have into bright or dark. If we're talking about something that look like a picture, is it bright or dark based on the observations of input layers? That's exactly what we're trying to do here. Okay, so applying neural networks. Okay, how can we apply neural network? I want to take us into real application now. Now, the real application, you're taking my class now. Okay, you're taking my class now. And you now ask yourself, will I pass this class? Okay, will I pass this class? That's categorical, right? It's either you pass my class or you fail my class, right? Okay, now that's categorical, right? Okay, now you now identify 2 features. Okay, 2 features, that may influence, you passing or failing my class. Maybe the first feature we're going to call that X1, which we call the numbers of lectures you attend. Okay, and X2, hours spent on the final projects. Okay, so if the class has a final project, and of course the final project is actually highly weighted, you get what I mean? So when you spend more time on the final project, of course, that will actually increase your chance of passing on the class. And what about the numbers of lectures you attend? Okay, so we've already identify two features now that may determine somebody passing the class, which is a classification problem, right? Classification problem in the sense that if we can get data set on these three variables on x1, x2, and y, then we will be able to generate a model that can actually be used to predict. When you have a new data point, if you have if you have somebody, if you have a student who have number, maybe we know the numbers of lectures he attend, and we know the numbers of hours he spend on the final project. Of course, we can actually predict whether he's going to pass the class or not. Okay, so as part of the preliminary investigation, we can decide to plot x2 against x1, the hours spent on the final project against the numbers of lectures you attend. Okay, you may want to see what is the relationship between these two variables. Okay, am I going to spend more hours on my project depending on the numbers of lectures I attend? Stuff like that. And as you can see here, the scatter plot that we have is not linear in nature, right? Where the green one is those who eventually will pass the class. Though, here we're actually using data set, we're using historical data. Okay, we have data point on those who actually already passed the class. It's like three students failed the class eventually from the data set we're actually going to use. And of course, 1, 2, 3, 4, 5, 6, 7, 7 students actually passed the class out. That means we are using 10 data point, right? uh, we have x1, which is the number of lecture they attend. We have x2, the hours spent on the final project, and we have y, which is categorical, whether they pass or not. So take a look at that. Okay, so let's say, for instance, we have a new data point. Okay, somebody that is not part of this class, and we spend for maybe the person actually spend we attended lectures 4 times, and he spent 5 hours on the final project. And we basically want to have we want to predict whether he's going to pass the class or not. And that is the reason why it's not having the color of green and red for now, because that's a problem. That is a tax, that we're fixed with. We basically want to predict this guy based on this feature. Now, to do that, okay, based on the feature now, the x1 is 4, the x2 is 5. Don't forget the x1 I said here, the x1 4 is the number of lectures the person attended, and 5, the numbers of hours he actually spent on the final project. And of course, we basically want to have a we haven't seen on his result. We don't know whether he passed or not, but based on these two features, we basically want to make a classification, and of course, and we're going to make a prediction. And when we want to do that, of course, we're basically going to use the idea of perceptron. Okay, we're going to put that into the network, and at the end of the day, we actually predicted zero, the 0.1, because the prediction here is going to be between 0 and 1. Then the 0.1 here is basically going to be telling you it's likely that he failed the class, when a number is very close to, when the predicted value is very close to 0, actually means it's more likely to fail the class. And when it's close to 1, it's more likely they pass the class. Okay, but you know what? When we look at the score of this person, he actually passed the class. So which means at time the net, depending on the weight, okay, and the activation function that you use, okay, we're actually going to have a loss. Okay, just like in using statistical framework, we also have errors. Okay, so we could also experience situation whereby I think I'm actually going to call it misclassification. Okay, so the loss, so this is what we call loss, and we should have a way to quantify loss. I'm going to take you back to statistical framework when you are using linear regression model, where you actually want to characterize relationship between variables. Of course, we know the model, we don't have a perfect model. We basically want to capture reality, but there's always going to be error. Okay, in statistical framework, we normally talk about error when we try to minimize error, we quantify error, we estimate that, we made an attempt to minimize that. And also in machine learning, in deep learning, in artificial intelligence generally, is the architecture, the algorithm they are using is not perfect as well. Okay, we have a loss. Okay, and how can we actually quantify the loss? I know they also want to minimize loss, and if they want to minimize loss, they're basically going to be looking for what is it going to be the optimal weight that I'm actually going to assign to each input variable to guarantee minimum loss. Okay, so we also do that in this, using the neural network framework. Okay, so the loss of our network measures the cost incurred from incorrect predictions. I'm going to say that again. You know, when you have incorrect prediction, just like this guy now, the model actually predicted, the architecture predicted 0.1, which means this very guy that attended lectures 4 times and spent 5 hours on his final project, the architecture actually predicted that he has a very high chance of failing the class. And what happened in the actual sense, he actually passed the class. Okay, so the loss is going to be the difference between the predicted and the actual. Of course, that is also what we have in the using statistical framework, where the error is going to be the difference between what happened in reality and what your model actually predicted. Okay, so, and that is the reason why to quantify that loss, okay, so we basically going to call this predicted and actual. So which means if you take a look at the predicted, you're basically going to see that it depends on the functions that we're using, the activation function and the weights. Okay, the way we assign weight. And that is the reason why in the subsequent lecture, I'm actually going to walk us through how we can actually figure out the optimal way that we guarantee minimum loss. You get what I mean? Just like, the approach that we use in a linear regression, where you're trying to estimate parameters in the linear regression, where you use a least square approach. The least square approach, the statistician believe the method can actually lead to drastic reduction in the error. The error that we made from the statistical framework is how we can minimize the unexplained variation. So we also do the same, in artificial intelligence generally. So what you're actually seeing here now is a weight. We're basically going to, depending on the activation function that we're using the other time, I show you, we got a segment function, tangent hyperbolic, and so on like that. Okay, so the loss function now will be able to compare, we're able to subtract the predicted from the actual. Okay, that is a way to quantify that. Okay, now if I have so many data points, okay, which is the combination of x1 and x2. Don't forget, the x1 is the number of lectures attended, and the x2 is actually the numbers of hours committed to find a project. Don't forget our y here is basically, um, you know, whether a student is going to pass the class or not. And of course, we already have our actual values. The 0 and 1 here is just values to depict whether a student passed the class or not. One actually represents student passing the class, and zero represent the student not passing the class. And of course, when we put this into network architecture, using the appropriate weight and appropriate activation function, at the end of the day, we're going to have an output. So what I have here is an output now. So why do I put a cross here? Because this particular student, 4-5, actually passed the class. That's why you see one. That was what happened in reality. But the model actually said he has high probability of failing the class. So in this data point now, the prediction here is there's a kind of a misclassification here. But when you take a look at the next one, for somebody who attended lecture uh, twice and spend 1 hour on projects, the model actually predicts that he actually has high probability of passing the class. And what happened in reality, he actually failed the class. So that was why you see that. And when you see the next one, somebody, the 5 and 8 now, he actually attended lecture 5 times, and he committed 8 hours to the final project. And of course, the model predicted that this guy has a chance of passing the class. And what happened in reality is pass the class. So that was why I put a question mark. That was why I actually marked that, right? Okay, so if you have a lot of data set like that, what you're actually going to have an avenue to compare your what the model predicts and what happened in reality. And with that, you'll be able to quantify the error loss. Okay, so since there's possibility, on each data point, we're basically going to have error incurred. Then we can actually try to obtain what I call the empirical loss. The empirical loss there is actually going to measure the total loss over the entire data set. Okay, so that is so like I said, this is a predicted. Okay, don't forget the predicted is going to have set of inputs with a weight, and you're going to use an activation function. You're going to have a result, and this is what happened in reality. You calculate your loss by subtracting, the predicted from the actual. Then you average that, you sum that together, you average that, and what we're trying to, that's what we call the empirical loss. And of course, we're trying to minimize that. You get what I mean? Okay, so there's something that we call the binary cross entropy loss in artificial intelligence generally, that can actually be used with models that output a probability between 0 and 1. Don't forget, we're working on a classification problem where the level of the response is categorical. And of course, we're actually going to have the predicted, even though the response is going to be 0, 1, 0, 1, 0, 1. I mean, the actual response, don't forget, we're using a supervised learning approach where for every input, we have, the output label, and the F of S now is the predicted result. The predicted result is not going to be 0, 1. It's just going to be something that lie between 0 and 1. We're going to have like decimal. We are very close to 1 is telling you there's high chance the student is going to pass, and very close to 0 is telling you there's high chance the student is going to fail. And of course, the cross entropy loss is actually this, where this is going to be the actual, you're going to have a predicted, the actual, you got a predicted. So the JW, when you put this into consideration, that's what we call the binary cross entropy loss. So this is what we're actually going to use when we're working with a classification classification problem where the level of the response is categorical. Okay, and of course, this is the code in Python. If you basically want to compute that, okay, if you attend my Python class, of course, I'm actually going to walk you through, using data set, how we can use Python to figure that out. Okay, now another thing is what we call another measure is of loss. It's what we call the mean square error loss. Of course, this mean square error loss is uh, very common in statistics, particularly when you are dealing with a classification problem. We also use it here. Well, let me tell you this: when you're talking about classification problem in you know, uh, we we use empirical loss when we use a binary cross entropy loss when you're talking about classification, where the level of the response is between 0 and 1. But in general, okay, in general, like for instance, maybe you are not talking about classification problem. Maybe the nature of your response variable is not categorical, it's continuous. Okay, like if I may decide to change the response variable here instead of labeling that 0, 1, and 0, where 0 represents those who fail the class and 1 represents those who pass the class. I can decide to change that from categorical variable to continuous, where I'm basically going to use the percentage that is the final grade of the student in percentage. Okay, that is what I have here now. So if I want to talk about loss, if I want to quantify loss, okay, I'm actually going to be using what I call the mean square error loss. So which means the type of error loss you're basically going to use depend on the nature of the response variable. I'm going to say that again. The type of the error loss you're basically going to use depend on the nature of the response variable. If you are working with the 0, 1, where the response variable is categorical, you're basically going to use a binary cross entropy loss. But if you are working with, or if your response variable is not categorical, but is continuous, then you're basically going to use a mean square error loss. And in that situation, the 90, 20, 95, and so on are the rescore. They are the observed score, the original scores of the students. Why this guy, they are just the predicted scores by the model, putting into consideration the numbers of lectures attended by a student and the numbers of hours committed to final project. Okay, when you take a look at this is a formula of the mean square error now. The yi here is going to be actual grade of the student. And of course, this is a predicted one, right? That is a predicted, like here now, you're trying to say, okay, 90 minus 30, okay, you square that plus 20 minus 80, you square that, 95 minus 85, you square that, and after squaring that, you sum that, then you divide by the numbers of that. That will give you the mean square error loss. A very good model should actually have a very small mean square error loss. Imagine if on the same question, you use different types of activation function. Maybe in one you use sigmoid function, and in the other one you use target and parabolic function. You now decide to compare error mean square error loss. Of course, the one that gave the minimum mean square error loss is going to be deemed to be a better model. Some of you may be wondering, why do I put this here? Okay, what happened in reality? The student scored 90%. This student that actually attended lecture 4 times and spent 5 hours on the final project, the model predicted the student to have 30%. Why? What happened in reality is 90. And that was why I put a cross, right? And the model predicted this guy to have 80%. But what happened, what the student got in reality is 20. Why do I put a pass mark here is because there's a kind of agreement between what happened in reality and what the model actually predicts. Of course, for all the data point, the peer data point we have, we basically going to have that. And if you want to implement that using Python, of course, this is the code that you're basically going to use in Python. And so, of course, I'm actually going to walk you through this in my Python class. Oh my God. Okay, so what is next? Okay, what is next? What I'm going to walk you through next time is going to be training neuron network. So in the training of the neural network, we basically going to know we don't just choose weight. Okay, for every input, there's going to be weights, right? Assigned to each of that. How can we actually, how can we actually figure out the weight that we walk? Okay, I'm actually going to walk you through that because the weight that we actually walk, the weight that can guarantee a drastic reduction in loss. Okay, so make sure you stay safe and have a very lovely day. Bye for now, everyone.